All right, let's get started. Good afternoon, everybody. Welcome to another wonderful uh, afternoon of organic chemistry. And Joshua, I'll get you in a second. Who's ever got, there we go. Let's start again. Welcome to another exciting afternoon of organic chemistry with your host, me, Dr. White. Important announcement. I think I'm stifling a sneeze. Hopefully that did it. But anyways, at right after class around 4 o'clock, I will send out an email with the password for the test number 1 PDF file, which I posted sometime yesterday. I think it was yesterday or Saturday. It was yesterday in D2L, the assignment area. Download it. I also have a file, both Word, MS Word, and PDF, how to make single PDF files with your cell phone. You don't have a scanner. And I will ask you to do that. Now, if you don't have a printer, relax. All I'll ask you to do is write your answers on a piece of paper. Make sure you put your name on it, everybody. Make sure you put your name on it. Upload, take pictures with your cell phone, then upload it if you don't have a scanner. If you do, use your scanner, and then upload it to D2L. Therefore, if you don't have a printer, like mine died end of last semester. It took me a while before I got that one. If you need a cheap printer, not cheap, inexpensive, that HP printer I have was like $200 delivered from Staples, and I love it. It's fast, it's monochromic, black and white, but it works well. All right, so you'll upload your test. When you're done, you have till 10 a.m. tomorrow. Please be on time. And in the email I'll send, the password is there. It's all lowercase, you can't miss it. After class today and after I send the email, I didn't have time this morning. I got to go spend some quality time with my driveway. But after I'm done with that, I will be checking my email frequently today. I'll also have my office hour tonight. If you have any problems with the questions about tests, either email me or stop by my office hour. If we were face to face, I would do the same. I would take you out in the hall because my hearing is not the best and tell me your question. I will not give you the answers to problems, but I will clarify things if you're, how should I say this, not are confused by a question of mine. And after tonight's test, or you take the test, you'll understand why I call them practice problems. All right. Now, depending on my schedule tomorrow, I'm going to try real hard to get them graded, posted to Blackboard, and then what I'll try and do, and I may not have time to do it before Wednesday, is also send you a individual email with each score points you got for each answer you put on a test. I'll get that done, but normally that's why I have my test on Wednesday, because usually I'll get it done by Sunday at the latest, usually a lot earlier. If I get it done, then Wednesday we'll go through the answers to test 1, which I always do. If not, we'll do it next Monday, because I don't want to go through it until you see what you got right and what you got wrong. Any questions? Let's see. Joshua, if you've got to leave early, that's okay. I'm sorry to hear that. I understand. I'm sorry to hear that, Thomas. You have my condolences. If you need extra time about test number 1, let me know. We'll work something out. All right. With that, if there's not anything else to be going on, let's get going and get to work. Now, what I'm talking about today will not be on test number 1, obviously. This is test number 2. Now, we've been talking about alcohols. And I believe I mentioned phenol. We've done nomenclature of alcohols. We also did the common names here, and I talked about phenol, which you probably pronounce phenol. No, it's phenol. I've had running arguments for a decade at a company I worked at where we used a lot of phenol, and I believe I was right, but that's another story, another day. Now, when we talk about alcohols, an important concept you should be familiar with is hydrogen bonding or hydrogen bond. And that's a weak force in water because of the electronegativity of oxygen and hydrogen. There's a very slight, and this is lowercase delta, means little difference, and negative charge or positive charge, this one, and each hydrogen. If we take another water, same thing. And there's a very weak attractive force, which we call the hydrogen bond. And generally, molecules with similar molecular weights have similar boiling points. And if you notice, I have a bottle of water here. And the water, by the way, my room, my office, is about, I don't know, about 65 to 70 Fahrenheit, somewhere in that range. And it's a liquid. If you look at other molecules, the same molecular weight that don't hydrogen bond, they're all gases. And hydrogen bonding causes water to be a liquid at room temperature, which is important. Otherwise, how would life evolve on our planet? Well, that's a question for another class, not mine. Well, it turns out alcohols can hydrogen bond. If we look at alcohols, remember, alcohols, ROH, where R is anything with carbon and hydrogens, have the same thing. Oxygen is more electronegative than hydrogen. There's a slight positive charge on this hydrogen. The oxygen is slightly negative. And if I write my alcohol this way, you can see the same thing. And there's a very slight hydrogen bonding or hydrogen bonding. And that plays an important role in different things. And this weak intermolecular, inter means between molecular molecules attraction, happen. We'll talk more about it when you have non-bonding electrons on nitrogen, oxygen, or fluorine, and each one of those atoms has a hydrogen on it. And alcohols can hydrogen bond with each other, and they can hydrogen bond to water. And that affects the water solubility of alcohols, especially the lower ones. Oh, by the way, don't go into a bar and tell the bartender, you know, you can make me a mixed drink because the alcohol can hydrogen bond to the water in the drink. Bartenders don't like being taught organic chemistry. Trust me. So that means most alcohols are either liquids or solids at room temperature. And they're lower molecular weight ones, and we'll talk more about this when we do a lab on alcohols, are soluble in water. Now, another important thing is the acidity. And again, I'm going to turn the switch off for the previous slide and this one. It won't be on a test or final, but stuff I would like to talk about. And if we look at the acidity of something, classic acid is a proton donor. And the ability to give up a proton, donate a proton is what an acid can do. Now, if we look at methane, this is non-existent. It doesn't happen because methane doesn't want to give up a proton. This is very unstable. But if we look at an alcohol, it can give up a proton, but it's a very, very weak acid, almost like water. The majority, actually it's weaker acid than water, exists here. This is very rare, doesn't happen, but it's good to know this because it'll explain some things. Now, interesting enough, and I'm going to go to my whiteboard because I need more room. Phenol, the hydrogen on phenol, I haven't asked in a while. Everybody see my whiteboard now? Thank you. All right, is a strong acid. And you can pull this off with a good base to form, this is called the phenoxide anion. Now the question is, why does this happen more with this than an alcohol? Because I can draw other resonance forms. And the more resonance forms you make, and I can draw two more, do not copy this down. I'll just do one more because Dr. White's having some fun. My last patent dealt with phenol and how I could use it in ways nobody else could. And the more you can draw, the more stable something is. So by making this more stable, the phenoxide anion, you make this a stronger acid. Oh, it's show and tell time. How many of you are familiar with this product? It's very nice in the winter. If you put it on your lips, you feel that tingly feeling. If you look at the ingredients label, you probably can't see it. You'll see phenol. And phenol is an acid, and that tingling is what you're feeling. The fact that there's a mild acid in there, small amount, but it's enough to give that tingling. Plus, that's also what helps it make it healing. Too much phenol can kill you. I worked at a company where a worker, unfortunately, pipe burst and he wasn't in proper protective gear and it killed him. Sad. It shouldn't have happened. So the phenol is a weak acid, but much stronger than alcohols because of resonance stabilization that I showed you. See board, you just saw it. All right, now, alcohols can function as weak base, which is off on this slide. What's a base? Something that's a proton acceptor. And alcohols, because the non-bonding electrons on oxygen, which we normally don't show, can react with acid. It's a very weak base, but it can form under the right conditions this. If you notice, there's something in that molecule I just drew that looks familiar. Right there. And what's HOH? Water. And it turns out this is an important mechanism for certain reactions because you can lose water and form this, which is called a carbonium ion. since about 1990s, they now call it a carbocation. I like the old name and still use it. The carbonium ion, I just think it sounds cooler. And this intermediate, we will learn, is quite important in the reaction of various things. But what I just drew here, I will never ask on a test. All right. Coming chapters or new functional groups, I'll be introducing you to how you name them, where you find them. I did a few in nature in our daily life. Where you find alcohol, ethanol? Well, your gasoline contains it, and also it's in some of my favorite things like vodka. But anyways, and therefore, next, we've done nomenclature, and now I'll go into two areas. One, how do you make alcohols? And two, the fun part, how do you react them to make new things? All right, how do you make an alcohol? Well, at this point, with what you know, you take a double bond, react it with acid and water, you form an alcohol, a carbon with a hydroxyl group on it. This is an alcohol. And this is the only reaction I'll have on more than one test. I can put it on test 2, as well as I will put it and have put it on test 1. Oh, I gave that away. Shucks. And let's do a couple, since we've already done this. And who's ever got a question, I'll look at it in a second. And the answer is yes, because it's a double bond reaction. So Joshua, not the alcohol, but just a reaction, okay? And as always, all questions are good ones. But like I said, this reaction I can put on there. And the question would be, give the organic product or products for the following. And remember, double bond reacting with acid, H plus is acid, catalyst, and water, remember, is HOH. And you break the pi bond, one carbon gets H, the other gets OH, and it follows Markov-Nichols rule. And that is the carbon with the most hydrogens on a double bond gets the hydrogen, the other gets the hydroxyl group. The rich get richer. Oops, no, it's right. And the poor get poorer. This has 2. This has 1 hydrogen on the double carbons, a double bond. Therefore, do you break carbon-carbon single bonds? No. But I can break pi bonds, and I just did. And this carbon right here has the most hydrogens. So I'll get the hydrogen, the other will get the hydroxyl group. And you know there are 4 bonds to carbon, so you can put in the hydrogens. And why don't you try this one for your fun and enjoyment on this Monday afternoon? All right, looks like everybody's done, so I better get to work. And if you look at a molecule, you should always look for what's different. What's not a carbon-carbon single bond, what's not carbon or hydrogen. And it'll even help you for test number 1 you'll take after class today. Double bond. What am I reacting it with? Acid, catalyst, and water. Remember, water is HOH. And you break the pi bond. One carbon gets H, the other gets the hydroxyl group. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. I have a methyl group on the second carbon. I broke the pi bonds of the 2 carbons as a double bond. And which one has more hydrogens? This has 1. This one has 0. Which is a greater number? Hope we all picked 1. So the hydrogen goes here. The hydroxyl group goes here. I know there are 4 bonds to carbon. And remember, it's your solemn responsibility to let me know if I make a mistake when I put in hydrogens or anything else. And that's how you do it. Since we've already done that reaction in alkenes, I'm not going to go any more over this one. And now let's talk about reactions of alcohols. And the first one is if you take any alcohol, and that's what this is, and it has on an adjacent carbon a hydrogen. Then if you react it with sulfuric acid, and this little triangle means heat, and I put down, just so you know, you got to really heat this high. On a test, I'll just put the triangle, but you really heat the heck out of this. 180 degrees Celsius is quite high for chemical reactions. A lot of them usually only heat 100, 140. So this is getting up there. And you lose water and you form a double bond. Now, there are possibilities if you have a carbon on this side with a hydrogen, which do you follow? And this follows Zaitsev's rule. I will never ask you what is Zaitsev's rule? And Zaitsev is another great Russian organic chemist, but you should know how to use it. Now, in the book, you would see something like the major product in an intramolecular alcohol dehydration reaction is the alkene that has the greater number of alkyl groups attached to the carbon atoms of double bond. Don't write that down, please. You look at that and you go, what's going on here? Well, hopefully when I'm through, you won't go, what's going on here? Now, listen carefully. This is one of the more challenging reactions I'll teach you this semester. Relax, take a deep breath, let it out, take another one, relax. Today you may not get it. After test 1, we'll do it on the problem set also. I'll go through another, but I'm only going to go through one example now. So after the test, we'll do it again. And this is challenging, but you'll get it. Everybody see it on the screen, the alcohol? Thank you. All right, now, when you look at this, you say, what's different? What's not carbon? What's not hydrogen? Ooh, look, hydroxyl group on a carbon. And adjacent carbons both have hydrogen. And the reason I'm writing it this way, not ROH, is because this is a dehydration, sulfuric acid, and heat. And it'll be high heat, but I don't have the right temperature. And you get a double bond, and it follows Zaitsev's rule. Oh, by the way, quick side note, about 2 years ago, I think it was, I was watching hockey. Dr. White loves hockey. He's a Blackhawk fan. I saw Bobby Hall play in his prime. My father took me to the games. And the championship, I didn't go to the game, but I wish you couldn't get tickets. It's almost impossible. When the Hawks won 61 Stanley Cup. Anyways, I saw on TV a couple of years ago, one of the players in the back of his back was Zaitsev. I wondered, is he a relative of the great Zaitsev? I never asked because I didn't see him. I wasn't there live. All right, so let's look, how do we do Zaitsev's rule? Now, here's the carbon with the hydroxyl group. Notice on this carbon, we have hydrogens. I'll call it A. On this carbon, I'll call it B. If I lose a hydrogen from carbon A and the hydroxyl group, I will form this molecule. Let me give me room for both. So I'll form between this and this carbon, carbon-carbon double bond. Do you break carbon-carbon single bonds? No. So I have 4 across. I have this methyl. I've now made my double bond, and I'll throw in my hydrogens. Doesn't sound scientific, but I put them in. All right, now, if I look at this carbon, which has a hydrogen, and this carbon with the hydroxyl group, if I lose that hydrogen on B in the hydroxyl group, I'll still have 4 carbons across my methyl group, and now the double bond will be there. Now the question is, which do you get? And here's how you do Zaitsev's rule. On here, you look at the 2 carbons and say, how many carbon atoms, again, how many carbon atoms are directly bonded to the carbons of double bond? In A, it's 1. In B, here are my 2 carbons. How many carbon atoms? You don't count these, just the carbon atom directly bonded to carbons of double bond. Well, here I have 1, 2, 3. Which is the larger number, 1 or 3? Hopefully you all picked 3. Therefore, what you get the way I will teach it is B is your correct answer. Now, in real life, which I won't teach, because I'm making it easier for you, you get about 90% of this and about 10% of this or even less. This is the major one. This is the minor. But we're not going to do that in my class. I'm going to make it easy. So Zaitsev's rule, this would be the product you get. And that's how you do Zaitsev's rule. Let me do one more. I'll let you try it. And why don't you try this one? If you react this molecule with sulfuric acid and heat, what would you get? Remember to use Zaitsev's rule. You get the molecule that has the most carbon atoms directly bonded to the carbons of the double bond. Why don't you give it a try? This is pretty challenging, so if you're having trouble, I'll give you about 2-3 minutes, and I'll jump in and do it. So if you're not getting it right, relax. This is one of the more difficult things I'll teach you this semester. All of you with pets, you can always bring them to class. This morning, I had a teacher class at COD, and this one woman that was amazing. She's got 4 kids, and she's got two, uh, like, what's the big breed like Saint Bernard? I'm doing, oh, not Doberman. I think they're Doberman pinchers, real big dogs. It's always amazing. Uh, she hasn't obedience trained them because she doesn't know how to. My sister was into competing in obedience training, so all her dogs are always obedience trained. All right, anybody need more time? If you're done, give me a thumbs up. All right, I think everybody's done. Let's do this. If we look at this molecule, what's different? Hydroxyl group, alcohol, but since I'm reacting with sulfuric acid and heat, I know if I have a alcohol and on the adjacent carbon, the one bonded to it, I have a hydrogen, I can have dehydration, loss of water, and this follows Zaitsev's rule that the carbon, you get the double bond that has the most carbons bonded to the carbons of the double bond. And here's my carbon with the hydroxyl group, alcohol, and here are my two adjacent carbons. And let's call this uh, A and B. Now, if I lose the hydroxyl group, and notice that does have a hydrogen, you just don't see it, and lose a hydrogen from A, I'll still have my ring. I'll still have my methyl group. I'll form a double bond between these two carbons. Now, if I lose the hydroxyl group from here and lose a hydrogen from B, remember there are two of them here, I would get this molecule. And when I do this, I usually write it on paper. I could do it in my head, but I still like to do it in paper because it's easier to see. Now, if we look at this molecule A, how many carbons are bonded to the carbons of the double bond? 1, people forget this methyl group is, 2, 3. So this has 3 carbons bonded to the carbons of double bond. In B, how many do we have? 1, 2. You don't count these, it has to be directly bonded. And the question is, which is the larger answer? Hopefully you pick 3. So the answer to this problem is A. And that's how you do Zaitsev's rule. And let's move on. Like I said, this is challenging. If you're not getting it today, I will come back to it. All right. Time to do some easier, fun reactions. So enjoy. Now, next one, you take any alcohol and react it with an acid, HX, where in real life and all, this is either chlorine, bromine, or iodine. What happens is you replace the hydroxyl group with the halogen and make an alkyl halide, which we'll learn later in the semester, something useful. You also make water. On my test for this type of reaction, I'll give the organic product or products. If you want to put down water, you can, you don't have to. So let's look at some examples of this. And the question would be, give the organic product or products for the following. Remember, these are the building blocks organic chemists use to make things that we use in our daily life. Now here, look what's different. Ooh, carbon, oxygen with a hydrogen. This is an alcohol. Ooh, I got HI, that's HX. Remember, X can be chlorine, bromine, or iodine. You replace the hydroxyl group with the halogen. Now, this happens on the carbon that has the hydroxyl group, and R will be the carbon that has the halogen. In this case, what's R? 3 carbons. What's X? Iodine. Therefore, do you break carbon-carbon single bonds? No, I have 1, 2, 3. Which carbon has the hydroxyl group, the end one? That will now have the iodine. And I can put in my hydrogens. And that's how you do it. Now, sometimes I'll write it plus here, like this. And organic chemists sometimes would put over the arrow. Instead of this, I could have put this. Each one would be the same. So your turn. Give the organic product or products for the following reaction. All right, everybody see my whiteboard on the screen again? I was just setting something up. I'll do maybe half an hour after a break. All right, let's take a look at this. And what do we have that's different? Ooh, an oxygen. Remember, look for what's not carbon, hydrogen, or carbon-carbon single bond. And here I have an alcohol. All this, including this carbon, is my R group. I'm reacting with HX. Remember, X is a halogen. X can be, in this case, it is chlorine, bromine, or iodine. And replace the hydroxyl group with X on the carbon that has the hydroxyl group. So you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 across, methyl there. Here's my carbon with the hydroxyl group. It will now be the carbon with the chlorine. And this is my alkyl chloride that I've made. That's what, when you have a halogen in our group, we call that alkyl halide. Chlorine, chloride, bromine, bromide, iodine, iodide. Oh, let's do a synthesis problem. On test 2, unlike test 1, where test 1, I only have 1 synthesis problem. On test 2, I'll have usually 3. No more, that'd be cruel, unusual punishment. And if you follow today's news, the Supreme Court, even though he picked 3 of the justices, told Trump he had to give up his taxes to the district attorney in New York. Enough said about politics. So let's do a synthesis one. This is a fun part of organic chemistry. What would you start and react with HBr to make the molecule I have written there? Your turn. While you're doing there, let me just check something quick. Yep. I'm not sure what you mean, Joshua, so I can't answer what you wrote. Oh, you have to, accidental typo. Oh my goodness. Luckily it didn't injure me. No problem. I'm just always on high alert to try and always answer any question a student gives or asks. And when you're done, give me a thumbs up. It looks like all the thumbs went up. So let's do it. Well, how do we do this? What's HBr? That's HX. What's different in our product? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Oh, a halogen on a carbon. And I can write that as this. And what do I start with? Alcohol. Remember, X can be chlorine. In this case, it's bromine or iodine. And the carbon with the halogen came from the carbon with the hydroxyl group. So do you break carbon-carbon single bonds going this direction? No. So if I end up with a ring with a methyl group, I better start with a ring with a methyl group. Which carbon has the halogen? This one. And that will have the alcohol. And that's how you do it. And if you react this with this, you will get that. And that's how it works. And that's that reaction. Now, there's one problem with this reaction. And what I'm going to write down, you do not have to write down. I'll never put it on a test. But say I want to replace that with, say, chlorine. And you say, oh, no problem, I'll react it with HCl, and you'll replace that. But wait, I also have on this molecule a double bond, and that will react, because I know alcohol will react to give me, in this case, let's do this. Let me just change it a little. And that should just clean this up. Again, you don't have to. A double bond reacting with HX, hopefully you know for later today. Break the pi bond, one carbon gets H, the other gets X, and it follows Markovnikov's rule. So you might get some of what you want, but more likely what you'll also get What you don't want is this molecule. And you might get combinations where only the double bond reacts, and you wouldn't even get this. If I'm trying to just get this to react and there are other functional groups present, what do? Well, guess what? You come up with another reaction. And that's what I wish I knew who discovered this. And that's what happened. And that's the reaction of an alcohol with SOCl2. This is called thionyl chloride. I'll never ask it to you. You replace the hydroxyl group with a chlorine. You also get SO2 and HCl, but that you can neutralize in this kind of reaction easily. So this wouldn't react with a double bond. And this will not react with a double bond. So let's do one real quick because it's about time for our break. If you do this reaction, I've worked with thionyl chloride. It's nasty stuff, but it does a great job. We look at here and say, what's the organic product or product? Look up here, what's different? Ooh, an oxygen with a hydrogen on carbon, alcohol. What am I reacting with? Thionyl chloride. What happens? You replace the hydrox group on the carbon with the hydrox group with a chlorine. Therefore, I have 1, 2, 3, 4 carbons across, 1, 2, 3, 4 carbons across. The end carbon has the hydroxyl group. The end carbon will now be bonded to chlorine. And that's how you make that. And with that, let's take a 5-minute break. I'm going to do some stretching. I'll see you at 1:55. Ring, 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 ring. Time to start. All right, we're talking about reactions of alcohols. Remember, an alcohol is a group where you have a carbon with a hydroxyl group, OH. And I showed you this reaction, where if you take an alcohol, react it with thionyl chloride, you replace the hydroxyl group on the carbon that has the hydroxyl group with a halogen chlorine. And I think because of cost considerations, I've never seen other halogens like a thionyl bromide or iodide. And it's your turn to have some fun. Dr. White shares, and that is give the organic product or product for following reaction. We're getting deep into organic chemistry if you haven't figured that out by now. And you're doing it. You should be proud of yourselves. And when you're done, give me a thumbs up. Those of you who don't have your camera on, webcam, give me a thumbs up with your emoji if you can. Thank you, Anna. I see it works for you out in there without the webcams. So let's do it. All right, what do we have that's different? You look at a molecule, look for what's not carbon, what's not hydroxyl group on a carbon alcohol. Remember, ROH, R is anything with carbon and hydrogen, hydroxyl group on a carbon alcohol, plus thionyl chloride. You replace the hydroxyl group with a chlorine, and therefore, do we break carbon-carbon single bonds? No. We have 4 across plus a methyl, 1, 2, 3, 4 across plus my methyl. Which carbon has the hydroxyl group? That one, which will be this one, and it's replaced with a chlorine. And that's how you do it. Now, let's do a synthesis part, one, because that's the fun part. what would I start with to react with thionyl chloride to make that molecule? Your turn. And when you're done, give me a thumbs up, however you can, with showing it on your video or your video feed your webcam or with the emoji. Thank you, Cynthia. And don't forget the lab that you did last Wednesday is due this Wednesday. You got plenty of time, but please hand in labs. They're easy points. All right, let's take a look at how do we do this. We look at here and say, what's different? What we're trying to make, what's different? Oh, a halogen, meaning what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. And this is a halogen. Remember, X can be chlorine, bromine, or iodine. And I'm reacting what with thionyl chloride to make an alkyl chloride? And the answer is an alcohol. Now, the carbon with the halogen will be the carbon with the hydroxyl group. Do you break carbon-carbon single bonds going from here to here? No. So if I end up with 4, I better start with 4. Which carbon has the halogen? This one, which is this carbon, which will have the alcohol. And that's how you do it. Now, one of the exciting things about my class is you're going to learn a lot about the real world because Dr. White, me, worked in the real world. We're in chemical industry, so I know how things go. And remember the first day I asked, how many of you are here? Why are you learning organic chemistry? And everybody raised their hand because someone told you have to take that. Well, guess what? Why are we learning that? Why are we really learning that? Well, now we're getting into the juicy stuff that I can take, show you. And from now on, you should be asking yourself the question, why am I learning this? And besides the obvious, because you want to get a good grade, because you want to get into school or a program, why are you learning this? Let's look at the last 2 reactions. How many of you have heard of artificial sweeteners? I think most of you have. And one of the more popular brands is Splenda. I don't get any money back from that company, but it is a popular brand. And if we look at Splenda, everybody see it on your screen? Thank you. You'll see it's a molecule that's got 0 calories, and your tongue tells your brain, this is good, it's sweet. Well, the key ingredient in Splenda is, all right, where is it in here? Sucralose. And sucralose is the molecule that's really in Splenda that makes your tongue tell your brain, oh, this is sweet. Now, here's the structure of sucralose, which is this, and you don't write this down. Each bend in the line is a carbon. And here's a carbon there. If you notice, it has a lot of alcohols, but it also has this halogen chlorine, this one right here, and this one. Now, why is it called the common name sucralose? Because it's made from sucrose. If I can spell it right. And sucrose, which you also know as table sugar, is this molecule. Now, it looks like sucralose. How come? Well, if I go back here, there's this chlorine on this ring, chlorine there, and a chlorine there. Notice this is a 5-6 membered ring. And what I'm saying is this hydroxyl group, this hydroxyl group, and this hydroxyl group have been converted into chlorines. How do they do that? Well, it's a trade secret, but I would pay money that one of the two reactions I just taught you is how they do it. And think about it. The building blocks, the general reactions I'm teaching you are used by companies to make products that they sell a lot. I think Sucralose has like almost $1 billion a year sales, some phenomenal amount. Now, this is a personal thing, so I'll explain to you the following. Do I have hard evidence about what I'm going to tell you? Not really, sort of, but not really, but I still believe it. All right, number of years ago in the New York Times, these two stomach doctors, I can't pronounce that name. I'm an organic, we don't say those. But anyways, did a study, and they studied the effect of sweeteners, artificial sweeteners, on the flora in the probiotics in your stomach. And the way they did that is they measured how much afterward in your stool. I think you know what I'm talking about. And they also had some of their friends do that. And they found something astounding. That is, whenever they drank something with an artificial sweetener, like Equal or Splenda or the others, or when they consume food with that, it kills off most of their probiotics, that important stuff in your gut that helps you digest food. Now, Dr. White's way beyond his level of expertise. Now, if you haven't noticed, I'm not a skinny guy. I've never been skinny. But anyways, no, maybe when I was born, I might have, I don't think I was even that. But anyways, for many years, I drink a lot of tea, and I still drink a lot of tea and other things, and I'd have artificial sweeteners in there. A couple of years ago, I went down the wrong path and made some kimchi that I did something wrong. It gave me food poisoning. Not a fun time. And when I went to my doctor, he's telling me, eat this, and you'll get over it. And I asked him, I just saw this article in the New York Times about how Splenda and artificial sweeteners really mess up your probiotics, the flora in there. Said, yeah, I saw that too. Said, my stomach doesn't like those. It tells me no. Even chewing gum with artificial, so I stay away from it. And this guy was skinny, so I wondered, what do you need artificial? But anyways, I was going to ask. A great doctor, unfortunately, I had to retire because of back problems. But I said, all right, well, I'm going to give up my artificial sweeteners like in my pop and everything and go back to sugar. And I expected to gain weight like that because sugar's got calories. Guess what? I didn't. And other things will still make me gain weight. But by switching back to sugar and stop eating anything, I found there was a dramatic change in this not gaining weight as quickly as I could in the past. And that's because I wasn't killing off my probiotics like was in there. And therefore, my personal thing, I stay away from artificial sweeteners now. In fact, right after that happened, I had about 2 cases of Verner's and Dr. Pepper in my house that were artificial sweetened, low-cal. And I brought them into one of the schools. I brought them to COD. And a woman there who was the secretary at the dental clinic, I said, just pass it out to anybody who wants it. And I got rid of it in a, how should I say, a friendly way. But the reactions I'm teaching you are used by companies in our daily life to make things you use. All right, let's look at an important reaction, oxidation of alcohols. Now, before I talk about this reaction, there's something I have to teach you, which is important. I will not ask it on the test, but it's no language I will use. When we look at alcohols, there are 3 types. Now, these three types are all alcohols. You have a carbon with a hydroxyl group. Now, let me introduce you to something new that I'll be using throughout the rest of the semester. I've taught you what's R, anything with carbons and hydrogens. But what's this R prime and R double prime? Well, just like in math, you have X, Y, and Z. Well, if you want in a molecule R's to be different, this to be different, we use the prime. Sometimes you use subscript number or letter if you have a lot of them, and I've used those in patents. But for this class, R prime and R double prime, and I think I have later on in the semester, I'll use a triple prime. Yes, I will. So let's go back and look at these three types of alcohols. Now, if we look at the first type, notice I have one R group on the carbon with the hydroxyl group, and we call that a primary alcohol. And organic chemists abbreviate that. Primary, one with a superscript like the degree, and alcohol. Now, if we have two R groups, they can be the same or different. That's why I use R prime and R. We call that a secondary alcohol. And we abbreviate it to degree sign ROH, which is how you shorthand alcohol. And the third type is, notice we have one, two, three R groups. They can be the same or different. That's why I have R, R prime, and R double prime. And we call this a tertiary alcohol. And we abbreviate it 3 degree sign ROH, alcohol. So we have primary, secondary, and tertiary alcohols. And I needed to mention that because I'm going to be talking about them in the following reactions. I will never ask on a test what's a primary, is this a secondary alcohol or tertiary, but it helps for you to identify it, know their names. All right, let's look at the next reaction. If I take a primary alcohol, which I could write like this, and oxidize it. Now, O in brackets means oxidizing agent. Now, if this was a 2 semester for chem majors, I'd be teaching you those and you'd have to learn them. And you'd have to learn oxidizing agents like potassium permanganate, sodium dichromate, and also potassium dichromate, and there are others, are oxidizing agents. I'm not going to ask you to learn this. What I will ask you to do is when you see the symbol O in brackets, that means oxidizing agent. And why is that? Because oxygen was one of the original oxidizing agents. What happens here is you lose a hydrogen there and a hydrogen there, and you form a carbon-oxygen double bond. And this is a new molecule you get. And later on, I'll teach you, this is an aldehyde. By the way, Dr. White loves aldehydes. You'll learn that when we get into aldehydes. So this is a general reaction. Alcohol, oxidize a primary alcohol. And you get an aldehyde. You lose the hydrogen here, hydrogen there, and you form a carbon-oxygen double bond. And so if you look at this reaction, the question will be, what's the product or products for the following? And if we look here, what do we have? Ooh, alcohol, a hydroxy group on a carbon alcohol, but we're oxidizing it. So it's important to know this is a primary alcohol. And what I'll get is I'll lose this and this hydrogen. I'll form a carbon oxygen double bond. And I like to write it this way as opposed to this way. Both are correct, but I think this looks cooler. And so that's why I'm going to write it. Plus, Dr. White's a world authority on aldehydes. My first patent was something I could do with aldehydes that nobody else was able to do until I did it. All right, do you break carbon-carbon single bonds? No. Here's my R group. Here's the carbon with the hydroxy group. They're still going to be bonded. I started with 3. I better end with 3. The carbon with the hydroxy group will be the carbon double bond to oxygen with a hydrogen here. And I can put in my hydrogens here. And that's how you make it. And why don't you try this one for your fun and enjoyment on this sunny afternoon? Yay, no snow. At least till Saturday or Sunday, I think. Even then, it might be part rain. Yay. And when you're done, don't forget to give me a thumbs up. Those who are quicker than others, please be patient. I try and give everybody time to finish. I think, is everybody done? Yep. All right, let's do it. If we look at this molecule, what's different? What's not a carbon? What's not hydroxy group on a carbon, but I'm oxidizing it. That's what the O in the bracket means. Therefore, I'm going to say this is a primary alcohol. One R group on the carbon with the hydroxy group, and that R group is this. And what happens is you lose a hydrogen there, hydrogen from the hydroxyl, and you form a carbon-oxygen double bond, which we'll talk more about when we get into aldehydes. And therefore, you break carbon-carbon single bonds. No, so I have 1, 2, 3 across plus these 2 methyls. 1, 2, 3 across, 2 methyls. This carbon is this carbon, so it's going to be double bond to oxygen. And I can put it into hydrogens. And let's do another one. Your turn. And you people without your webcam on, are you done? Give me a thumbs up. All right, thank you. All right, let's do it. What's different here? Ooh, oxygen with a hydrogen, hydroxy group on carbons, and we're oxidizing it. That's what O in brackets mean. When I oxidize a primary alcohol, what do I get? I lose a hydrogen there and hydrogen there, form a carbon oxygen double bond. I get an aldehyde, which I'll teach you more about. What's my R group? What's ever attached to the carbon with the hydroxyl group. Notice I have 1, 2, 3, 4, plus this carbon, 5. I start with 5. I better end up with 5 because this reaction doesn't break carbon-carbon single bonds. 1, 2, 3, 4, 5. Which carbon has the hydroxyl group? That one. And now I can put in my hydrogens. Remember, hydroxyl group counts as one bond to carbon. And that's that. Oh, let's do one more. Since the fun part of organic chemistry is synthesis, what would I oxidize to make that molecule? And this is how synthetic organic chemists like I have been trained and did and still do. If I want to make something, how do I start with it? Does that help? Got it? And as I mentioned, Dr. White has one of the fastest mouse wheel fingers this side of the Mississippi and the other. All right, anybody need more time? All right, let's do it. All right, now we look at what's different. First of all, oh, I'm oxidizing something. Look at the reagents. What's different here? Ooh, oxygen is double bond to carbon, and this is an aldehyde. What's my R group? Methyl. How do I make this? I start with a primary alcohol. What's my R group here? Methyl. So the carbon double bond to oxygen is a carbon in your starting material with the hydroxyl group, and R is methyl. So if I take this molecule and oxidize it, I will get this molecule right here. All right, hang in there, sports fans. I gotta close some things here. All right. Sorry about that. Once in a while. All right, we just said oxidation of primary alcohols, and you can have a secondary alcohol oxidized the same way. And if I have let me just do this. You have a secondary alcohol, which on my notes I have this way. Sometimes it's hard for my software to do that, but I can write it out with a notepad. If you oxidize a secondary alcohol, which is what this is, lose this hydrogen, you form a carbon oxygen bond. And here what you get, this is called, and I'll teach you later in the semester, a ketone. So primary alcohol, aldehydes, secondary alcohol, ketone, you can draw it like this or like this or like that. Here, bending the line tells you they're carbon. More likely, I'll draw it this way in class, or another way, which also you could have drawn. These are all ways, and I'll teach you this. And therefore, I better mention something. In a couple of chapters, you'll learn Dr. White loves ketones and aldehydes. They've been good to me. I've been good to them. And at that time, I'll teach you about, how many of you have heard of comfort food? You know, when you're feeling not good, like low and eat some of the comfort food, it makes you feel better. Well, Dr. White has comfort functional groups. Yes, I do. Now you know I'm an organic chemist. All right, let's take a look at the following. Now I can write, and I'll do this in class, this alcohol like this, or I could show bond angles and write it like this. Since there's free rotation around a carbon-carbon single bond, I can write it either way, and I do. And if I take this and oxidize it, which is the same as taking this as oxidize it, what do we have different? Oh, look, a secondary alcohol. Same thing here. And what do we have? Secondary alcohol, oxidize it, lose hydrogen here, hydrogen there, form a carbon oxygen double bond, which is known as a ketone, and that's what you got. I can call this R prime. Another way of looking at it is, here's the carbon, this carbon, which becomes, or this carbon becomes this carbon. And one way of showing it, lose this hydrogen and this, form a carbon oxygen double bond. My R groups are still attached to that carbon. This is one way. Same molecule. Here's my R. It doesn't matter what you call R prime or R. They're still attached to that carbon. And this would be double bonded to oxygen. Which one of these is correct? They both are. And organic chemists sometimes will do that. Now, let me show you one more thing. And now we're getting into the good stuff. If we look at this reaction, what is different? Ooh, look at a molecule, look for what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, hydroxyl group on a carbon. Notice I have carbons here and carbons here. This is a secondary alcohol, but it so happens my two R groups are connected in the ring. And what happens, and don't forget there is a hydrogen, we don't show it there, but there is. When you oxidize it, there's this hydrogen to the carbon with the hydroxyl group, you form a carbon-carbon double bond. Well, am I going to break carbon-carbon single bonds? No. Here's my carbon right here, which is this carbon, which becomes this carbon bond, double bond to oxygen. And we show that like that. And that's called a cyclic ketone. It's a ketone in a ring. You can't have an aldehyde in a ring, but you can ketones. Dr. White and Mother Nature love cyclic ketones. We'll talk later on in some of your hormones. Yes, your steroids, there are cyclic ketones, and we'll get that near the end of the semester. And why don't you try this one for your fun and enjoyment on Nicer Weather Monday. Oh, excuse me. I seem to have caught the yawns. All right, let's get going. Looks like everybody's done. What's different here? Oxygen with a hydrogen, hydroxyl group on this carbon. Notice we have carbons on that carbon. And that's a secondary alcohol. If I oxidize it, I'll lose these two hydrogens, form a carbon-oxygen double bond, and made a ketone. And therefore, what's R? This. What's R prime? This. So this carbon, which is this carbon, which becomes this carbon, I'll form a carbon-oxygen double bond. So I have R, carbon double bond to oxygen, this one right here, and then another R group. And that's how you do that. Oh, let's have some more fun with this stuff. Dr. White's on a fun kick. And when you're done, give me a thumbs up. All my camera people did a thumbs up. How about the rest of you? All right, looks like everybody's done. Let's do this. What's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Oxygen with a hydrogen and a carbon. And this is being oxidized. And if we look at this carbon with the hydrox group, I got carbons here, it's a secondary alcohol. Oops, already got a prime. And I'm oxidizing it. I form a carbon-oxygen double bond. What's attached to those? That carbon is still attached to it. So we're talking about this carbon, the whole ring is attached to it. So I have my 5-member ring. I still have my methyl groups. They're not going to disappear. They're coming along for the ride. And the carbon here, that was this carbon, now becomes this carbon, which is how we show it. And the question is, what would you start with and oxidize to make this molecule? This is called synthesis. This is the fun part of organic chemistry. Dr. White likes synthesis. Well, you should figure it out because I'm a synthetic organic chemist. Uh-oh, I think everybody's done. You people are out your camera on. Are you done? You are. All right, let's do this. What do I have that's different? Carbon, double bond to oxygen. It's got carbons here and carbons here. I'll call one R prime. I can call this R prime, doesn't matter which you call which. What do I have to oxidize to make this a ketone? And that's an alcohol. And that's a secondary alcohol. And notice I have 4 carbons here. I better start with 4 carbons. The carbon that's double bond to oxygen is a carbon that has the hydroxy group, the center carbon. I can look at this as R prime and R, which it is, and still attached to that carbon. And I know there are 4 bonds to carbon. And that's how you do it. Now, let's look at a tertiary alcohol. Now, notice you're forming a carbon-oxygen double bond. Well, if I were to lose the hydroxyl group, and do that, it can't happen. Why? Because there'd be 5 bonds to carbon. That's never going to happen. So that means the answer to this problem when you oxidize a tertiary alcohol is not this. The answer to that question is no reaction. Tertiary alcohols cannot be oxidized. This is a tertiary alcohol. It can't be oxidized. So the answer for that, if I were to put it on a test, no reaction. But I'll never put it on a test. Why not? When I was an undergrad, both in general chemistry and especially organic, if the teacher asked on a test, give the product or products, and the answer was no reaction, I didn't like that. That's not fair. You're asking me, what does this make? Well, it should make something. So therefore, Dr. White teaches by my golden rule of teaching, don't do to my students what I didn't like done to me. So I'll never put a reaction on a test where the correct answer will be no reaction. If I ask you to give the product or products, it's going to react. So I'll never put that reaction on a test because it doesn't react. Oop, wrong thing. If I look, let's talk about, and we'll talk more about this after a break because it's coming up in a few seconds. You can have alcohols with more than one hydroxy group. And I'll talk about these when we come back afterward. I see this is about time to take our break. So come back at 2:50. That's when, if you have to leave, I'll be posting a video so you can make up anything. Life happens. Unfortunately, I had a student this morning at my other class. She works at a nursing home, and because 2 of the patients died and some of the workers were exposed or potentially exposed, they couldn't come to work, and she put in like 100 hours last week. She was doing double shifts, and a nurse, that's got to be tough. And because of some lab she handed in late, I understood why, or hasn't gotten it in. But take a 5-minute break. I'll see you in 5 minutes. Ring, 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 ring. Let's get back to school. I'll get you back. Welcome back. All right, let's continue our discussion of alcohols. And when we talk about alcohols, so far I've just talked about molecules that have one functional group in them, but there are others you can have. There's a whole group of alcohols where you have two hydroxyl group, and they're called glycols. And I'll just talk about one glycol. That's the simplest glycol. It has the common name, not the IUPAC name, of ethylene glycol. And ethylene glycol, first of all, is a poison, but it's an important molecule in our daily life. We say it about everything. Well, this one is. How so? Well, how many of you like the fact that in the winter, your radiator hasn't frozen when it got real cold outside? That's a good thing. How many of you like in the summer, your radiator, when it got super hot outside, didn't start boiling? How is that so? Your antifreeze is a mixture of glycol and water, and that gives an effect and colligative effect. Remember I told you about melting point depression? Well, at the same time, you have, I better get full screen on this, you have boiling point elevation. So that means the solution of water and ethylene glycol have a boiling point that's much higher than water and a freezing point much lower than water, which is why you don't have to worry about your radiator freezing, expanding, and bursting. Unfortunately, like happened at the water pipes into many people's homes in Texas. And that's ethylene glycol. Now, why did they color it green? If you've ever seen antifreeze, it's green. That's to tell people this isn't water because it's a poison. Ethylene glycol is a poison, and by dyeing it green, we tell people, or the antifreeze industry tells people, don't drink this. Let's look at the next one, glycerin. Now, glycerin has three alcohols in it. And this is glycerin. And on test, I won't ask you this, but I thought I'd cover it anyways. And glycerin is a trihydroxy, or they call it a triol, tri meaning three, OL alcohol. Glycols are called diols, di-2-OL alcohol. And glycerin is an important compound in our daily life. Now, one of the things is, I'll teach you later in the semester when we get into fats and oils, when you eat anything with a fat or oil in it and you swallow it and it gets in your stomach breaks down the fat and oils. And one of the things it makes is glycerin. And I'll teach you later on, I worked for a company that made about 100 million pounds a year of glycerin and other things too. So Dr. White knows his glycerin. And glycerin also has three hydroxyl groups. And because it can hydrogen bond to water, it can attract water. It's one of the compounds that's safely used as a humectant. Humectant is a fancy word in the food industry that keeps water in products. How many of you like, they started, I don't know, maybe 10, 15 years ago. Now you can go to the supermarket now and buy in a package those nice, soft, super soft, chewy cookies, like chocolate chip cookies, which Dr. White needs like a hole in the head. But anyways, how do they make it super soft? Well, they put in a humectant, something that keeps the water from leaving the cookie to make it crunchy. And that's used in other things. I don't know if it's glycerin or another humectant, unfortunately, is used in cigarettes to keep the tobacco from getting real crunchy and dry. Dr. White used to be a heavy smoker, but I gave it up in 85. At one point, I used to smoke about almost 2 packs a day. Thank God I'd be dead now if I hadn't given up. Unfortunately, I killed my father, one of the things. At least I learned finally to give it up. Now, next one is sucrose, otherwise is table sugar. And it has this structure. Notice it has 1, 2, 3, 4, 5, 6, 7, 8 hydroxyl groups in it. And that's sucrose. This is table sugar. We'll talk more about it later in the semester when we get into carbohydrates, one of the three major food groups that we'll talk about in this class. We won't have a chance to talk about pizza, potato chips, or alcohol, vodka, and other food groups, but these three we will. And if you notice a lot of hydroxyl groups, we have a lot of hydroxyl groups that won't get you inebriated, like ethanol, which only has one, as a small molecule. So sugar is what we call a polyol. Many OL alcohols. Now, there's one other polyol I'd like to talk about. That's polyvinyl alcohol, also known as PVA. Now, I'll teach you later in the semester about polymers. And polymers are like a freight train where this is a repeating unit, N times CH2OH, CHOH, another CH2OH, another C, and so on, N times. Now, in polyvinyl alcohol, N is on the order of 500,000, ooh, that's big, to 1,000,000. And even a little higher, 1.5 million, but usually in this area. So that's huge. And you've got polyvinyl alcohol, PVA, in your home. No, I don't. Yes, you do, probably. Where do you find it in your home? Well, if you mix water and PVA together, you get this white stuff that helps glue paper and wood together, and we call that Elmer's glue. In fact, I worked for the company originally, started Elmer's glue. I worked for, at that time, it was called Borden Chemical, which you know about Borden Milk. They had already sold the milk division off long before I got there, even though a couple senior managers who had worked when it was the milk division was part of Borden Chemical or part of Borden, had beautiful collection of Borden memorabilia, like milk bottles from the 1880s and all that. Amazing. Not my thing, but it was still amazing to see. So next time you see Elmer's glue or the white glue, you'll know there's a lot of hydroxyl group alcohol polyol in there. All right, let's move on. I'm going to cover this real quick. Switches off. Click. Will this be ever on a test? No, but I still want to cover it. How many of you ever heard of antioxidants? And they're good for you. That's what medical science is telling us. And I try and make sure I get my antioxidants in my food. And what are antioxidants? Well, turns out oxygen, which is all around us and in us, you breathe, and your food and other things is exposed to oxygen in our air, will react with certain chemicals, like especially double bonds, which I didn't teach you when we went through alkenes, but they will. And they form a molecule, a functional group we call a radical, which I'm not going to teach you this semester. Dr. White could do a whole 2-semester graduate level course on radical chemistry, but they're very energetic intermediates or species that want to react with anything to make something else, more radicals. So they're pretty nasty functional groups to have around. Now, it turns out certain molecules that can interact with a radical and make it harmless or make themselves into what's known as a harmless radical. And those are antioxidants. And most of the antioxidants, first of all, I just explained here and everything here, and examples that you can have radicals where you don't want is in food and lubricating oil. And by the way, how many of you ever tasted or smelled potato chips that went rancid or smelled butter that went rancid? That's because of antioxidants weren't there and oxidation occurred. And you formed radicals that made that, ew, it doesn't taste good or smell good because it made new chemicals you didn't want. I think that's Mother Nature's way of warning you, don't eat this stuff. Something's gone wrong. Well, it turns out most antioxidants are phenolic compounds. Notice I use the word phenol as an adjective. That means they have a phenol ring in them. And these foods will react with radicals to form what's called stable radicals that won't do any damage. Now, 2 of the more popular ones that used to be used, they're not used as widely now, are BHA and BHT. And here on the screen, everybody see that structure? Thank you. This is butylated hydroxytoluene. It's a common name. This is a T-butyl group. This is a T-butyl group. Notice the hydroxy group on a benzene ring, phenol. You have another methyl group. And this for many, many years was used as the antioxidant in potato chips, except sad news, my mother never bought, oh, Mom, I should eat more potato chips because they have antioxidants. That's good for you. She didn't buy it. No, they're too fattening. Stop eating them. And unfortunately, she was right. But that's one of the reasons I like T-butyl groups. Now, if you've noticed, potato chips no longer keep BHA and BHT in there. Why? Because they found another way of keeping them fresh and not undergo oxidation to form radicals. And that is about 10, 15, 20 years ago, organic chemists found a way of making a film or the packaging for now potato chips that didn't let oxygen through. And that was a major breakthrough. That's also why, if you look at mayonnaise bottles now, they're plastic, or before they also was glass, because of the same reason. The other thing they now do, now that they have a barrier for their package that won't let oxygen through, is before they package it, they blow in some nitrogen. And the nitrogen blows out any air that's in there. They seal it off with the nitrogen, and packaging keeps the oxygen. And now you can have fresh potato chips that don't have antioxidants, but still taste real good and last long, and their package be a lot longer than the old days, than when they had to use antioxidants. And now you learn all the joys of organic chemistry. Now, one other thing, and this has been, how should I say, postulated that, and I have no idea if this is true or not, but it's interesting. One of the reasons antioxidants are good for you, theorized, and this is really, I don't know if it's valid or not, but I've met some medical scientists have put this forward, is radicals help age you and also cause other problems in your body. And by eating antioxidants, you tie them up and inhibit that. Now, I don't think if you start eating tons of antioxidant containing foods, you will grow younger or live longer. Who knows? But it's an interesting theory. All right, it's new functional group time. Fire up, people, new functional group. Unfortunately, the functional group I'm going to teach you about now, how can I put it any other way? It stinks. I mean, it stinks. I mean, it stinks. And that functional group is the thiol. Now, the thiol is like an alcohol, except you have instead of the hydroxyl group, you have SH, a thiol group. THI is the newer IUPAC way of saying sulfur. Now, where's the thiol? Here's the thiol, a sulfur with a hydrogen on a carbon, and this is a thiol. Now, until about, I'm guessing the late 80s, 1980s, they used to be called mercaptans. And sometimes Dr. White will still, because I grew up with that name when I was learning organic chemistry, will call them a mercaptan, but they're a thiol. And it has similar nomenclature alcohols, which I'm not going to teach you or ask you to learn, but instead you find the longest chain with the SH on it, take the alkane name, drop the E, add THIL and a number if they need them. The most important thing about thiols, they stink. Boy, do they stink. How stinky? Well, you'll see in a second. Now, the old IUPAC name was mercaptan, which used to be what sulfur compounds were called. And I'll still use it because that's what I grew up with. But last decade or so, 5, 7 years, I've been still pretty good calling them thiols. Now, when I say thiols stink, what's something stinky? How about an animal or a person that's got skunked? If you've ever been by where a skunk lets loose, oh my God. Oh, well, what do they use in their defensive weapon? Water and 2 thiols. And someone, don't ask me who, I wouldn't want to have done it. Analyzed this defensive weapon of a skunk, and this will never be on a test. And this unsaturated thiol, which has a trans bond, double bond, but notice SH on a carbon, thiol, it's about 45% unsaturated, and the saturated is the other 25%, and I believe the remainder is water. And this heated up a little and shot from a skunk. Oh, whoa, 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 that's awful. Thiols stink. Now, where else can you find thiols? Well, here I don't think they stink. Dr. White loves onions and garlic, and their odor is due to thiols. Now, up to now, switch has been off, switch is on. First of all, you should know what a thiol is in general, R with SH. And now I have to tell you a very sad story, and it's a true story. Back in about 1935, give or take a year, in Texas, a high school had a horrific accident. It blew up. There are 2 versions of the story. One is that when they built the high school, they're right near some oil refineries, and because at that time it wasn't considered anything valuable, they offered to just pipe the methane from when they generated made oil free of charge to the high school. And when they built the high school with the using methane for heating and everything, they were pretty sloppy and the pipes leaked. You're going to say, Dr. White, well, didn't they smell it? And the answer is no, because methane, CH4, has no odor. Now, that's one version. It filled the high school with methane over time. The other one is they're having some sort of social or fundraiser for the high school in their gymnasium, and right next to it was a kitchen, and it was a chili one. And the flames went out underneath the chili pots, and whoever ever watching it didn't, and that blew up. What do I mean by blow up? If you go in your house, and this is something because I've worked with hydrogen and have to know about, there are things that will easily cause explosions. Every time, you can't see it, but right over there is a light switch. Every time you turn a light switch on or off, click, there's a little spark inside, unless you have explosion-proof switches, which none of you do in your house. I don't. And if you have something flammable around and it's gotten in there, boom, you're dead. Well, that's what happened. One version is with the gymnasium, somebody turned on a light or lit a cigarette, boom, about 150 people were killed instantly, and many, many others were badly burned. The other version is it filled up the high school, and mainly in the woodworking class, when they turned on a drill press or a sander or whatever, click, electrical switch, boom. Either way, a lot of people were killed, a lot of people were severely injured. And because of that, Texas commissioned a commission, or had created a commission to find out how to make natural gas safer. And you should know, they put in a thiol, T-butyl thiol, I almost said mercaptan, and T-butyl thiol stinks. How stinky is it? They only put in 1 pound, 3 to 4 pounds of that per every billion pounds of methane. That means you can smell. How many of you have ever smelled a gas leak? You know it's strong. Well, there's only 4 parts per billion, ppb, of a thiol in natural gas, and you should know this. You should know this. And that's why you can smell natural gas, because methane, natural gas, essentially CH4, is odorless. Now, in propane, they put a slightly different thiol, and a student asked me a couple of years, how come that smells differently? And I said, I'm not sure. So I looked it up, and because it's a liquid in a tank, and the solubility in propane, they use a slightly different thiol, but it's stinky too. Now, do I have time? Yes, I do. When I was in grad school, I went to Michigan State, and when I started, it was a pretty brand new building. Now it's decades old, because that was back in the 70s. Oh, I shouldn't have said that. But anyways, and the building, it was fantastic. It was 2 blocks long, full city blocks for this chemistry department. It had 5 stories and a penthouse. Then it had a basement, a sub-basement, and a sub-sub-basement. It was huge. We had something like 450, 500 grad students and faculty working in there full time, plus all the students. And once a month, we would have a surprise fire drill. And you took it seriously in a chemistry building, because there was a lot of stuff that could blow up or catch fire easily. Well, this was November, and luckily I was not teaching, but I was in my lab, and my jacket was nearby. Fire drill, stop everything, I put on my winter jacket, went out, because it was sort of a drizzly, cold November day. Well, anyways, fire department shows up, and that was unusual, because usually for a fire drill, they don't. And then we're out there 5 minutes, 10 minutes, 15, 20 minutes. I walked over to one of the firemen and said, what's going on? Where's the fire? And he said, gas leak. So we go back, and all of a sudden one of us, and I don't think it was me, but it could have been, what idiot poured T-butyl thiol down the sink? It turned out a new grad student in inorganic did that. It went down the sink, went down the drain, and then in one of the sub basements, which one of the water traps had dried out, so some of the fumes came out. A janitor smelled T-butyl gas leak and called the fire department, which it was the right thing to do, and got the fire department. We finally, after about 20 more minutes, got back in. They figured out what it probably was. Uh, oh, in the chemistry department, we had a ward you never wanted to win, which I didn't, luckily, never did. It was called the Alfred E. Newman What Me Worry. And we had a nice big thing of Alfred E. Newman. If you've ever seen Mad Magazine, you know who I'm talking about. And that was called the Alfred E. Newman Award, and that was given to the grad student each year who did the stupidest thing in the world in a lab. And that guy won it hands down. But remember, T-butyl is added to natural gas to give it an odor. And next time, if you happen to smell gas, that's to make you aware there's a leak, because if it wasn't there, you wouldn't know, and you could have a serious disaster wherever, living or working. Uh-oh, you know what time it is? It's new functional group time. New functional group. We're moving along quickly. And what's that new functional group? I got to open up the chapter when I had to close down. Hang in there. And that new functional group are ethers, and we'll also talk about in this chapter epoxides. So this new functional group is ethers, and I'll tell you a story about the Civil War. I'll tell you in this chapter a story about Dr. White, and then I'll get into something you said, he's talking about that? And the answer is yes, I can. Now, what is an ether? An ether is where you have an oxygen with two R groups attached to it. Come back. And this is an ether. An ether, you have an oxygen with two R groups. They can be same or different, R and R prime. If you look at the molecule I just drew there, that's an ether. I call this R. I call this side R prime, or I can reverse it, and that's an ether. Now, it turns out most people use ethers never use IUPAC nomenclature, including Dr. White, even though I know it. And we use the common names for ethers and name each R group of an ether as the alkyl group is attached to the oxygen, where R was an alkyl group, then add the word ether at the end. See board for examples. Uh-oh, I better get to work. Now, this is one of the rare times where I'll ask you to give it a common name. More likely, I won't even ask that. I'll ask you to draw it. But what do? You look at the molecule, what's different? Oxygen. Carbon's here, carbon's here. Ether. And now, if I look at this R group, oh, that's a methyl group. This one, R prime isopropyl. Therefore, how would you name this with a common name? You could call it methyl isopropyl ether, or you can just as easily call it isopropyl methyl, because these are common names. There's no rule which goes first, which goes second. So let's have you try one. Give the common name for this compound. Just a quick reminder, about 10 minutes after class, I'll send out an email with the password for test number 1. And you'll have until tomorrow morning to hand it in. Please be on time, and I will try and get it graded and the scores posted in D2L by the end of the day. If I don't send out an individual email with your points for each answer you put down, I'll cover on Monday, not Wednesday, the whole test and go through the answers, which is why I normally give tests on Wednesday, but I didn't want to wait a whole other week. I don't think that would have been fair to you. All right, I think everybody's done. What do we have here? We have, an oxygen with carbons here, and this is an ether. How do you name this? You name each one of these as the R group, as the alkyl group it is, and doesn't matter which goes first. I'll call this ethyl, and then this is N-propyl, and the answer is ether. Oh, this is easy. And if you had to draw the structure, start this way, ether, ethyl, and methyl. So it doesn't matter which side you draw it, because molecules are not frozen. That would be methyl ethyl, or I could have this as easily, and all I'm doing is rotating it around. Write it that way. And that would be methyl ethyl ether. Oh, let's do one for you. And this would be diethyl ether. Draw the structure of diethyl ether. Remember, di is 2, tri is 3. And when you're done, give me a thumbs up. All right, looks like everybody's done. And if I go this way, ether, I know that's this. And what are my R and R prime? Di means 2, ethyl. Therefore, both R and R prime are ethyl group. And this is diethyl ether. Now let's talk about diethyl ether. Diethyl ether is probably the most widely used ether. And a lot of people just call it ether. Just like, how you call tissue paper Kleenex, it's sort of the same way. And diethyl ether is an excellent solvent to do reactions in. Ethers are pretty inactive, unreactive themselves, and that makes them a great one. I use the very specialized ether, in my research when I got my PhD. It's called tetrahydrofuran. I'll show you the structure, but you don't have to know it. Well, it turns out diethyl ether has, they found about 1840, a very interesting property. When you inhale it, it knocks you out, which if you're a doctor and you've got to operate on somebody and you don't have any way of putting them under, and they got to be awake while you do something. In the Civil War, where they did a lot of operations to remove bullets and unfortunately amputate soldiers' legs and arms, they found ether. There's one problem. Ethers are flammable. Ethers make gasoline look like water. That's how much more flammable. So if you're a doctor, even up to the 1900s, early 1920s, and there was any spark or flame around, one, if your patient had ether in their lungs, you just lost your patient. Also, if there was ether vapors around, and ether vapors have a density higher than air, so they tend to stay down here. They don't float away like other hydrocarbon, like from gasoline do. This stays there, and you now have a big fire, and you just lost your surgeon because his hands have been burned badly. So what happened? Well, it turned out organic chemists, yay, found if you replace some of the hydrogens in the ether with halogens, it still knocks people out, but it's no longer flammable. And since you're only using a small amount and you're not continually exposing people, patients to it, it's not, you don't have to worry about the potential being a carcinogen. Hold on while I find something real quick. This one, sorry about that. Does everybody see on your screen the isoflurane? And it has this structure. Notice you have an ether. This carbon, every bend in the line or intersection is a carbon, has two fluorines plus a hydrogen. You don't show it. This side has two carbons. This carbon has three fluorines. This one has a chlorine. How did they decide that was the best? I don't know. But to this day, this is a inhalation anesthetic. Do I have time? I do. Now, many years ago, when I moved into the house I'm in many, many years ago, Dr. White, not always being smart, was moving heavy boxes of books when I moved in. And all of a sudden, this doesn't feel good here. I went to a doctor and said, you need to go to a surgeon. And a friend of my sister's knew a real good surgeon. And lo and behold, I had a hernia problem. I popped it. Oh. And on a further examination, he said, you know, your other side's about ready to go too. And I had a double hernia operation. And it was in a hospital in Evanston, because at that time, where did I live? Well, that's where the surgeon operated, and he was quite good. So from Schaumburg, I went over there. Well, anyways, my surgery was scheduled for 1 p.m. and about 12:30, they come in, they get on a gurney, get the gown on, they wheel you, and I'm outside the operating room. I'm just laying there, and time's going click, 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 nothing. I can see a clock, it's 1 p.m., and I'm wondering what's going on here. And finally, the anesthesiologist was very nice, and he came to me and said, I see you looking concerned. I should tell you about your doctor. What's wrong with my surgeon? Well, he's never on time. He's got a history of never being on time. He's always late. So guess what? He's running late. Well, being a nice guy, the anesthesiologist was, he asked me, what do you do for a living? I said, I'm an organic chemist. Oh, really? And he brings over the bottle of one of the anesthetics I'll be using on you. And it was that isoflurane. I started telling him, you know what the structure is, because I could see it on the name on the label. He said, I got to get to work. I said, what's up? Can't you tell your doctor here? You know, they're all wearing masks and uh, good news. I survived, even though I was on the operating table 4.5 hours. Something I want to forget about, but the doctor said, boy, you had it bad, but I sure fixed it good. And that was more than 20 years ago, and I've never had a problem with it. And so that's my story about anesthetics. Now, I'm turning the switch off totally on this slide. Everybody see IUPAC on there? Thank you. All right. Just in case you were wondering, yes, IUPAC has rules for this. Name the smaller group of the ether as an alkoxy group. I'll explain this in a second. Name the larger group as per an alkane nomenclature, and use the name and number as the alkoxy group as if it were a substituent. Now it says see board for example. Let's do one here, this right on here. This will never be on test. Now, the common name for this ether would be methyl and butyl ether or N-butyl methyl ether. Now, the IUPAC, the longest chain is 1, 2, 3, 4. This whole thing is called an alkoxy group. Which will never be on my test, but if you ever encounter it, and that's RO bond to something, is called an alkoxy. And this is called methoxy. Longest chain is 4 butane. And on carbon 1, and this would be 1 methoxy. Butane. And which is easier to generate? Well, this, which is why all organic chemists use the common names, unless you have to put it in a legal document like a patent. All right, switch is still off. Physical properties, they're all low boiling. Diethyl ether, the body heat, your body heat will cause it to boil, and they're flammable, beyond flammable. If you've ever seen, I warned someone, they didn't listen to me, and luckily they didn't burn their face off or their hair. Some of the times you'll see people put diethyl ether into a carburetor of a car to help start it because it's so flammable, and it starts in pretty much any engine you have a spark, it will start it or help start it. Well, the guy was putting way too much, and I said, why don't you wait 10, 15 minutes? Because I happened to be going to the parking lot and saw what he was doing. Oh no. So I got in my car, or got far away from there, and where my car was, and all of a sudden you could see a big flame coming out of his engine when he had his friend try and start it. Luckily he had backed off a little, or I would have been calling the fire department for paramedics. But ethers are extremely flammable. Switches on. How do you make ethers? The Williamson ether synthesis. And here you take what's called an alkoxide, this, which you make from an alcohol. I'll teach you that in the lab, but not in the classroom, and react it with an alkyl halide. And this oxygen will bond to the carbon that the halogen, and you lose sodium halide, make a salt, and make an ether. And this is the Williamson ether synthesis. Dr. Williamson invented it, which is why we honor him. And if I asked on a test 3 points each, and again, test 2, not 1, what's the organic product or products? And this is how you make building blocks we use in our daily life. What's different here? Ooh, an oxygen with carbons, and it's got a negative charge, and it's got a sodium cation. I don't know why I always circle negative and negative positive. I don't know if there's a convention. But anyways, carbon, carbon, carbon. Ooh, halogen. I have RX, and they're different. And this is Williamson ether synthesis. And you'll form an ether. And I'll explain why probably Wednesday. And you get sodium halide. So what's my R group? Methyl. What's my R prime? And propyl. The carbon with the halogen is the carbon in R prime that's bonded to the oxygen. You break carbon-carbon single bonds? No. So my R prime is 3 carbons to the end carbon. And that's the ether I make, methyl and propyl ether. I'm about ready to sneeze, excuse me. Yeah, it ran away for now. No, I didn't lie to you. Excuse me. And what would be the organic product or product? You don't have to put down the salt, NaX, that you would get if you make this compound, or if you react those 2 compounds together. Your turn. Let me check something still. Yep, good. Now we're getting into the fun stuff of organic chemistry. Have you noticed I've been secretly brainwashing you to look for what's different in a molecule? And in all reality, organic chemists like me do that. When I look at a molecule, it's the first thing I look for. And when you're done, don't forget to give me a thumbs up. I think everybody's done. Anybody need more time? Nope. All right, let's do this. What do I have that's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single? Ooh, an oxygen with a negative charge, a sodium cation to carbons, and alkoxide. And yes, there's nomenclature for alkoxides, but I'm not going to teach you that. Ooh, carbon, carbon, carbon. Ooh, a halogen on a carbon, alkyl halide. Remember X here, I didn't write it up there, but I better, can be chlorine, bromine, or iodine. I've never seen fluoride, it'd be too expensive. And what happens is this attacks that, kicks it out, and you get an ether. And what's our ethyl? What's our prime? Isopropyl. Remember, the carbon with the halogen is the carbon the oxygen will be bonded to an R prime. Do you break carbon-carbon single bonds? No. So I have my R group, oxygen, then my R prime. Which carbon has the halogen, the center of 3? And we've just made ethyl isopropyl or isopropyl ethyl ether. Now, as I look at the clock, oh, I've gone over 30 seconds. Sorry. But anyways, don't forget in about 10 minutes or so, I'm gonna get up and stretch a little, get another amount of water in my water bottle, get something to drink. I will be sending you an email to your student account with the password for test one. Remember, download it from D2L. And I also have instructions how to make a single PDF. If you haven't done it already, by tomorrow morning, make sure you upload it with your answers. If you don't have a printer, you can just handwrite out just the answers. You don't have to write out all the problems. You don't. And with that, I'm going to say, Gain Gesund. I'll see you on Wednesday. We'll also do a lab on Wednesday. With that, bye. If you have any questions for next hour or so after I send the email, I'll probably be playing with my driveway, getting whatever snow that didn't melt off that. I also got to put out the garbage. And after that, about 5-ish or so, and also during my office hour and tomorrow morning, I'll check my email. If you have any questions, email me or stop by. With that, Gain Gesund. Goodbye.